Good morning to all. My name is V. Srinivaslu. I am currently pursuing BTech first year in Srinivas Ramanujan Institute of Technology. Now, I will explain about susceptibility and dielectric constant and relation between them. Let's dive into the topic. Susceptibility and dielectric constant. First, let me introduce about this. So, this presentation explores the relation between electric susceptibility and the dielectric constant. We will they delve into their definitions and their mathematical connections, the things to them. Understanding this relationship is crucial in electromagnetism. It helps explain how material respond to electric fields. First, we will learn about electric susceptibility. Electric susceptibility denoted by chi quantifies the degree to which a material polarizes in response to applied electric field. It dimensionless quantity that reflects the ease with the which a material molecule align their dipole moment with external field. A higher susceptibility indicates greater polarization for an electric field strength. Mathematical electric susceptibility is related to polarization P and electric field E, and by the equation P equals to E, where 0 is a vacuum permittivity. Understanding susceptibility is crucial for predicting material behavior in capacitor, insulator, and some electronic component. So we will learn about dielectric constant definition. So dielectric constant, often represented by kappa, is another fundamental parameter that describes material ability to store electrical energy in electric field. It is defined as ratio of electric field strength in vacuum to electric strength in material for the same charge distribution. Alternatively, it can be understood by the ratio of capacitance and capacitor with material as a dielectric capacitance with the same capacitor with a vacuum as electric. Dielectric constant is dimensionless quality as we know and is always greater than equal to 1. Material with high dielectric constant efficient as strong electrical energy. So now the relationship equation. The relationship linking the dielectric constant K and the susceptibility chi is given by K equals to 1 plus chi. This equation highlights a direct proportionality between the two. A material with high susceptibility will also have high dielectric constant and vice versa. The relation bridges polarization to macroscopic probabilities. Now I will show you the relation between D, E and P. As we know, D is the displacement and electric displacement, E is electric field and P is polarized density. So this is a written one from my notes. So let me explain this. Dielectric displacement is sum of dielectric displacement in vacuum and polarization. So as we know, D equals to D naught plus P bar. And we know that D naught equals to epsilon naught by epsilon. So mark it as equation 1 and 2. Now sub equation 2 in equation 1. So we will get D equals to E naught naught epsilon plus P. So now relation between chi and ER. So D equals to E naught epsilon naught E plus P bar, but D equals to epsilon naught ER epsilon. So now we will substitute this. So at last we get ER equals to chi plus 1. Molecular interpretation of susceptibility. At the molecular level, electric susceptibility arises from polarization of individual molecule within the material. So polarization can be due to the alignment of permanent dipole present in a polar molecule water or induction of dipole by applied electric field. The strength of these dipoles and their abilities to align with the field determine macroscopic susceptibility of materials. Factors influencing susceptibility include temperature and the frequency of applied electric field, which can cause resonant behavior. Understanding these factors is crucial for designing materials with tailored dielectric properties for specific applications. So, impact of capacitor. Inserting a dielectric material between the plates of capacitor increase the capacitance of by factor K. This is due to reduction of electric field and increased charge storage. The higher the dielectric constant, the greater the capacitance. This property widely used in capacitance designer. So applications. Now we will see about applications in capacitors. Capacitors are obligate in electric circuits and rely heavily on dielectric material to enhance their capacitance. Dielectric constant of the material between capacitor and plate influences the amount of charges can be stored for a given voltage. Higher electric dielectric constant leads to smaller, more efficient capacitor. Different dielectric materials are used in capacitor depending on application. Example includes ceramic for high frequency application, polymer for flexible capacitors, and electrolyte for high capacitance, low voltage application. The choice of dielectric is a key design consideration in capacitance manufacturing. So, dielectric material are crucial components in capacitors, insulators, frequency circuits. They are essential for energy storage on illustrations. So, now the key takeaways are the electric constant and electric susceptibility are intimately related. Understanding this vital for predicting material behavior in electric fields. They both fundamental concept in electromagnet and electric engineering. They impact capacitor design and other crucial applications. So thank you for giving this me opportunity.